this RL day, and he's all alone, so he'll be the sole defender of RL. We're also going to have, I thought, 2 verification talks, but Zico is still tossing coins, picking what he can. Then we'll also have this ethics, we'll have a couple ethics talks today in this ethics panel. I think none of the ethics speakers are here yet. So I have to say that this is also a wild card for me. I'm very curious how this will go. I've planted a number of questions up here. And feel free to throw in your own questions, since, of course, what ethics and deep learning means is even quite arbitrary. So yeah, please start putting anything you like up here. So yeah, let's go ahead and start with the first talk. So Lihong, like I said, will be our sole defender of reinforcement learning. First challenge.
So good morning, everyone. First, I would like to thank the organizers to invite me to come and talk about our recent work. Today, I'm going to talk about reinforcement learning via an optimization lens. In this talk, I would like to argue that there are some really interesting and fundamental research opportunities that lie at the intersection of reinforcement learning and optimization. In particular, we show that reinforcement learning can be formulated as a standard optimization problem with a clearly defined objective function that can be easily estimated from data and solved. This idea may sound straightforward to supervised learning audience, but in reinforcement learning, it turns out that the dominating approaches these days are based on a different approach, different class of approach. And in this talk, I'll explain why this is the case and what challenges these current approaches face and how we may solve it via an optimization lens. This talk actually has some overlap with the talks yesterday. I'll talk about them when I'm in the right slide. So reinforcement learning is about learning to make decisions from data. There are potential applications ranging from games to control and human in-the-loop systems. When people try to make reinforcement learning work in practice, there are a number of research problems that are involved. And today I'm going to, and particularly for this talk, I would like to take a very boring but hopefully basic view of reinforcement learning when we try to apply it. Very similar to other areas of machine learning, when you apply something to a real problem, there are 3 steps, major steps. One is data collection. And then you use the data, you train a model. Once you have the model, you test the model, how good it is. In the context of RL, the first step, data collection, corresponds to doing efficient exploration. And the second is to learn a value function of policy. And the last one, testing whether policy is good enough. There's also the counterpart called policy evaluation. And all 3 yellow boxes are non-trivial research problems, as it turns out. The majority of, well, many RL works these days are about online RL, where exploration of data collection is part of the algorithms. And for the purpose of today, I'd like to focus on the offline or batch RL part, where I assume that data is given beforehand, and what I want to do is to make the best use of data and learn the policy. And this is a very different problem, and today we're going to talk about the second block, which is value function learning from batch data. And this is helpful as it separates different challenges, and we can focus on particular problems and go deep into it. And also, this is useful this by itself can be very useful in practice, and in the long run, it can be used as a component to solve the full online reinforcement learning problem. So this is the area we're going to talk about today. And then, so this is the outline. I'll first go through some of these basic RL terminology and setup, and then I'll explain why the current approaches may go wrong in reality. And then I'll go and I'll describe a Primal-dual formulation for reinforcement learning as well as the new cardinal laws for solving value function learning problems. So MDP, MDP is Markov decision process. It's a model that captures a class of problems interaction problem between an agent and the environment. There's a set of states, a set of actions, and then the agent can take an action in any state and then transition to a next state following some probability and incurs a reward function for that transition. And there's a discount factor, and the goal of RL is typically to maximize the total reward discounted by gamma in the long run. And then here's a very simple, perhaps one of the simplest example of MDP, which is to find a deterministic shortest path in a finite graph. So here you can think of the nodes in a finite graph as states. Edges are actions that you can take from that node. And then cost associated with each edge is the immediate reward with the negative sign. So here we want to minimize cost, not maximize reward. And we want to find the shortest path with the minimum cost that goes from the start state to the goal state. If you solve this problem naively, you may have to enumerate all possible paths from source to target. This is very inefficient. Instead, you can take advantage of this recurrence equation that tells you the minimum cost to go from any node I can be decomposed as the sum of the one-step cost to one of its neighbors plus the minimum cost to go from that neighbor, j. And you have to take a minimum over all the neighbors. And this is the idea behind the principle of dynamic programming that was discovered decades ago by Bellman. And this equation allows you to decompose a potentially combinatorial and exponentially large solution space into a much smaller space, and then solve it more efficiently. More generally, we have this Bellman equation where now instead of a finite graph, we now have an MDP where the state space can be infinite, continuous, and the reward function, now we want to maximize reward, not the cost. And the transition is not deterministic, but it can be stochastic. But the same principle of dynamic programming applies, and we end up with the Bellman equation that looks very much like this one, except that you need to take expectation for the transition. And for the purpose of this talk, solving RL is roughly equivalent as solving the Bellman equation for the value function, the optimal value function V star. Okay. So this is the setup. Let me introduce one more notation, the Bellman operator, to make the following discussion easier. This is the Bellman equation. The right-hand side can be thought of as an operator that converts this value function into a new function that is defined this way. So that's how the Bellman operator is defined. For any function v, I can define the Bellman operator as this guy, and the Bellman equation is just saying that V star is the fixed point of this Bellman operator T. It's saying the same thing as the previous slide. This Bellman operator has well-known and nice properties such as monotonic. If you apply it to two value functions, one is dominated by another, the resulting value function is also dominated by the other one in the same direction. More importantly, it's a contraction, meaning that if you have two value functions, V1 and V2, you apply the Bellman operator, you guarantee that the max norm of these new functions are closer to each other than the previous one by a factor of 1 minus gamma. So if you apply this operator sequentially, then you reach a geometric convergence to something called a fixed point. Okay? And this fixed point turns out to be the unique fixed point and this is the optimal value function that we try to solve in the first place. And this is the mathematical foundation of most of the current reinforcement learning algorithms, including different versions of value iteration, TDQ learning, and some components and active critique. If you can solve this, you can compute this T Bellman operators exactly, at least on average, then you guarantee that eventually you can converge to the right solution. Okay, and these exact cases roughly more or less the same as assuming that the state space is finite in many cases. So things so far seem to look good. So what can go wrong is that when Bellman meets Gauss, when we try to approximate the value function in a large state MDP using a more compact, perhaps parametric representation. For example, you may represent V star as a linear approximation, the neural network, right? And then in order to represent the new value function after you apply the Bellman operator, which may, so this is the new function. After you apply the Bellman operator, it may jump out of the parametric family of function that you can represent. So you need this extra step of projecting the new function back to the class of functions that you may represent using your neural network, for example. And this composition of the two operators, projection and Bellman operator, unfortunately loses the contraction property, the gamma contraction that the Bellman operator enjoys. So and it's been known for decades that if you do this kind of thing, then the value of the solution, the value function estimate may diverge. It may oscillate, it may have different behavior, and they may diverge, even for very, very simple problems. People have tried different ways to solve the problem, and there is success in limited cases. But in general, this remains a very hard problem. So to give you an idea why this could go wrong, let me show this classic example from Tsitsiklis and Roy. You have two states. There's two-state MDP. You want to represent a value of the first state by W, and the second state's value by 2W. So W is the single parameter, the scalar that you try to learn. And suppose that you sample states x1, x2 uniformly. From the ith of x1, let's say you start from a non-zero W. For the ith of x1, let's say W is 1. It seems to the agent that going from W to W2, its value should be bigger because now after one step it gets $2. So, and my current estimate is $1. After one step I get $2. So I need to increase my estimate for this state because of Bellman operator, right? So now W is increased from 1 to something bigger than 1. You can, and this state has the will push the W down, but if your sampling distribution of these two states are the same, then you can show that when gamma is not too small, then eventually the whole system will be unstable and W will diverge to infinity. In other words, when you apply Bellman operator, there's some dilution or some bootstrapping effect that makes the agent, fools the agent so that the agent will think it has more and more rewards so that W can diverge to infinity. Does it matter in practice? This is a very simple example. In practice, this does affect practice. So these are a few typical examples from published papers. For example, you apply DQN on Atari games. You see this kind of very unstable behavior, which is very different from typical supervised learning curves. And sometimes you see the value function going up and down over time without convergence. And sometimes you see the value function the value goes up and then down, and then it's changed. And this is divergence behavior. And this remains a long-standing open problem, how to ensure convergent dynamic programming in the approximation case. This is perhaps the oldest paper I can find that is about functional approximation and dynamic programming in 60 years ago. So the algorithmic ideas is not new, but how to make sure that the algorithm is stable and convergent and reliable, it's a very challenging problem. And it's so difficult that it has this famous name called Deadly Triad by Rich Sutton and colleague. And then there's some recent efforts like emphatic TD, but it still remains unclear whether they can solve this problem. There's also the interesting work on removing delusional bias in Q-learning. But I think the focus is different from this work. The focus there is about how to ensure the policy class is consistent between multiple steps. But here, even if you have a single action, which means that there's no such delusional bias, this kind of non-stable behavior can still exist. So these are the problems with the existing approaches. Can we solve it by reformulating it as optimization problem? And the answer is yes. There are different approaches. One is linear programming. This is the Bellman equation. It turns out that it's equivalent to solving this linear program. If you remember that the T operator is a monotonic operator. So this constraint means that V is an upper bound, uniform upper bound on V star, pointwise upper bound. And this objective means that you want to make V as small as possible. So when these two are combined, the solution is exactly the value function you try to solve, V star. And there are a number of works in the last years. And yesterday, Professor Wang from Princeton talked about this line of work. And we'd like to, if you're interested, please watch her talk. And today, I'm going to focus on a different approach that tries to solve the fixed point directly. Again, we go back to this Bellman equation. We want to solve the fixed point. A very natural starting point is this. Right? We want to minimize the discrepancy between the left-hand side and the right-hand side. And you minimize this objective to 0, then you found a solution. But why doesn't people do this? Why didn't people do this before? It's because the objective function is not friendly. If you write it out, you notice that there are two things. One is that there's a max operator that makes the problem not differentiable. Right? It's hard to optimize using gradient descent, for example. And the second thing that is more subtle is that there's this double sample problem hidden by this conditional expectation. So what it means is that here, the objective function, and for this objective function, you need to compute a conditional expectation for this guy. So this is what we need, right? This conditional expectation. You want to do gradient descent on the parameter, for example. But when you observe the data are usually in the form of state, action, next state tuples, S prime tuples. So what you end up doing using, say, square loss minimization, using BP, using empirical data, what you optimize is actually this. Right? The expectation is outside of the square, not inside. So these two are different, and that difference gives you a bias gradient. And in practice, it make your value function converge to a suboptimal or wrong solution. Now, so how do we get around these two challenges? The first one is, well, people have used these ideas in different contexts to introduce a smoothing term, entropy regularization. So here we have a max of overall actions in the Bellman operator. We can equivalently write this max over action as max over all policies without this part yet. Okay? And then this smoothing is to add this regularization term so that the policy that we find will be smooth, meaning that it has non-zero probabilities to all actions for all states. And then with this smoothing, we end up with a smooth Bellman operator T sub lambda. And this T sub lambda has a nice property that is still a gamma contraction. So all these previous results of Bellman operator still apply, that we have a unique solution V lambda star, and we can find it. And this new solution and the previous solution we try to find are not too different. They're controlled by this lambda in the linearly. And more importantly is this temporal consistency condition that Dale and colleagues discovered in the path consistency learning paper that says that with this regularization, you can show that for all state action pair, if you find a solution, then this equation holds for all state action, even if the action is not optimal. So now you don't have to worry about the max over A in the objective function, because this is true for all A. So you can sample S, sample A, and then try to minimize the discrepancy between the left-hand side, right-hand side of the equation in the bottom.
The S on the right-hand side, one of them should be S prime, right?
Which? Oh, here?
Yeah.
Oh yeah, sorry, yeah, it's a typo. Thanks. Okay, so now we end up with this this new equation, which is from this one. There's a square error between the left-hand side, right-hand side. There's this one. Now I still have this this conditional expectation inside the square loss. How do I transform it so that I can be easily approximated by sample empirical data? So this is done by using a Legendre transformation. We denote this whole thing here by x sub SA. And then I use the reverse transform of the Legendre, the conjugate function. And so that by introducing a new variable y for each variable x SA. And then I end up with this new optimization problem that has this dual variable. And notice that here the y variable is a scalar, but here is a function on state action. And there's a mathematical subtlety here from this step to this step that depends on something called interchangeability principle. But the idea is to use this transformation to convert this x squared function into something that's linear in x, so that you can easily estimate this quantity using samples without having to worry about the quadratic thing. So after this long journey, we have now reached this new minimax or Primal-dual formulation. In a sense, we turn a fixed point of the Bellman operator into a settled point problem with this objective function, where this guy is the Bellman operator, the Bellman error, right? And this new is the newly introduced dual variable, or dual function. The good thing about this formulation is that now we finally have a clearly defined objective function that can be easily estimated from data. And then once you estimate it from sample, you can do things like stochastic gradient descent to optimize it until convergence. And you may wonder how we can solve this inner max. You can do different kind of things. For example, when nu is parameterized in a concave way, then the inner max can be solved exactly. Or you can do 2 time scale updates so that you can reach a stationary point, but the guarantee is weaker. But at least there's something, you can do different kind of thing by injecting different kind of structures to make this problem easier to solve. And by the way, we've been talking about square loss of Bellman error, but you can see that the same idea can be applied to other convex loss function as well. And the resulting algorithm is quite straightforward at this point. Once you reach this formulation, essentially what you try to do is to parameterize the dual variables and primal variables, 3 things involved, by, say, neural networks, and do gradient descent and gradient ascent on the primal and dual variables until convergence. And then another benefits of looking at the problem, framing the problem as optimization problem, is that now you can employ some of these standard techniques from statistical machine learning to analyze the behavior, statistical behavior, and optimization behavior of the algorithm. For example, this guy, this is the true value function. This is the solution I found using the previous algorithm after running it for n iterations. W is my parameter to learn. And I can decompose this error in a standard way, like optimization error, statistical error, approximation error, and this smoothing bias that I introduced. And you can quantify and upper bound these different quantities using very standard techniques, and then you can analyze when and how the algorithm work. Okay? So these are pretty standard, so I'm going to skip it, and you can. For example, you can get a standard finite sample convergence rate under certain assumptions. I would like to give some remarks on related work. This idea is, in a sense, similar to Bellman residual minimization. although in this previous work, the focus is on policy evaluation, meaning that the policy is fixed, and all you need to do is to estimate the value function. And once you do this, and then it's used as a black box inside a approximate policy iteration, is a meta algorithm to optimize the policy. And then the same primal-dual formulation can be used to derive a number of previous gradient TD algorithms that were derived historically using different principles. But now, using this idea, you can derive them from very standard optimization perspective without all this RL-specific intuition and expertise. And the third thing that I have talked about briefly just now is that these formulations allow you to use well-established techniques from machine learning and statistics to understand the behavior of the algorithm. And also, as I actually gave this talk 2 years ago at Simon's, the same place, that when you look at the problem in this primal-dual way, you can use some of these technology optimization techniques such as stochastic variance reduced gradient to reduce variance in a gradient descent and obtain exponential speed up in convergence rate. So these are this work is it's not new. It was done last year. So next, I would like to talk about something that was done recently.
Yeah, before you move on, you motivated your approach by saying that the standard approach, because of this projection, is no longer contractive. It loses all the nice properties of the Bellman iteration. So if you do experiments with this new one for DQN or something, does it behave more stably?
Yes, I will have experiments later in the slides. Yeah. Actually, in the next section. Yeah. It's very related. It also comes from the primal-dual formulation, but as a simplifying approximation. As you may wonder, when we formulate a problem as minimax, it's much like for example, a GAN problem where with optimization is known to be very hard to do. So can we simplify the problem?
Can I just ask a question about the previous stuff?
Okay.
Is it clear that generalizing the value function is what we want? Because what we want is the policy that we learn should behave similarly on training and test data, right?
That's right. Yes. So the short answer is that in this formulation, the primal variables are both v and pi. So we solve it. I've been saying v, but actually it's solving v and pi at the same time. And the longer answer is that there are other algorithms that solve pi directly without looking at the v. But then there are, in many cases, it's more effective to also take advantage of this v information. This is actually the principle of dynamic programming that allows you to solve the problem more effectively. Okay, so now can we simplify the primal-dual problem into a primal-only problem? And the answer is yes in some cases. To explain the idea, let me look at a simplified case where there's no action. Well, or the equivalent, the action set is has only one action. So I can remove pi and lambda and a, etc. in this formulation. And this primal-dual problem has this form. Okay, this is true without a, and this is the Bellman error without a, and the same thing here. And now my restriction is to restrict this dual variable to reproducing kernel Hilbert space, HK. In short, this RKHS is a Hilbert space where the inner product can be efficiently computed by a kernel function. And different kernel functions correspond to different RKHS. So after I do this, the nice thing to look at this is that you can think of this as a soft constraint that prevents this dual variable to be too big in L2 norm. Okay? This is a soft constraint. And then it can be approximated by a hard constraint Usually the soft constraint is easier to solve, but now I'm going to do the opposite way, where I replace this soft constraint by a hard constraint so that I restrict this nu to be in the Hilbert space, and it lies inside the unit ball measured by this kernel norm. And then I have this, but without this soft constraint term. And the reason I do this is that once you write this problem this way, using properties in RHS, I can show that this guy has a closed form, including this max. Max, the whole thing, has a closed form. And this closed form can be written in this way. Here, S is sampled from any data distribution that you have. Now, this term, I have another S bar that are also independently sampled from the same data distribution. So S and S bar are in IID. And then I compute the Bellman error for S, Bellman error on S bar, and weighted by the kernel function, the kernel of S and S bar. And take the average, and then you get the same thing as before. So now what I have done so far is to reduce the Primal-dual problem into a minimization-only problem. And the trick is to use the RHS property to find a closed form solution for the inner max. And now we end up with a new loss for solving Bellman equation. Let's call it L sub k. This is what I copied from the previous slide. Let's call this new function L sub k. Similar to the Primal-dual problem, it's also a well-defined objective function that doesn't require double sample. So I should mention that this is not double sample. It means there are two independent samples from state that you can get from looking at drawing two samples from your training set. What double sample means that the next state S prime, starting from S or S bar, should be doubled. So this is a different double sample. And this can be solved, estimated from data. And because of this, it has a well-defined objective function, and estimated from data, you can use, say, stochastic gradient descent with many batches to solve it. The paper has the details how to extend this case to the control problem when you also want to optimize policies.
Excuse me, I lost track of the operator R. Is that, it's affine in this case because you had a single action?
Which one are you talking about?
R?
The
Operator?
script R operator.
Oh, this guy. Yeah. Okay.
Affine and invertible?
Yeah, it's affine.
And also invertible? If so, right, this is closed form, right? Like the solution is the min, the inverse R of the minimum eigenfunction of K. It's just an observation, I was just wondering.
So, okay, so R is affine, but then, so let's go back to this. Maybe I misunderstand your question, but so from here, R is affine, but it's some quantity, some random some quantity, okay, some function. And then this function this whole thing with the max can be equivalently computed this way.
Yeah, it's okay. Yeah, it was just an observation.
Okay, so I'm going to talk briefly about what this function, what this loss function does. There's an interesting eigenfunction interpretation. By Mercer's theorem from the kernel theory, this kernel function can be written in this way, as essentially project this state is embedded in this, represented by these eigenfunctions, EI, and then weighted by this lambda I that are positive scalars. And with this decomposition, this L function can be, you can show that this LK is equivalent to this. What is this? This is the Bellman error for states. And what it does is to project this Bellman error onto these eigenfunctions, average over states. So this is a projection, and then square. So in a sense, this loss function is an Li weighted square L2 norm in space spanned by these eigenfunctions. And of course, you can imagine that different kernel functions lead to different lambda I, EI pairs. Okay. As an example, we can use a Gaussian kernel. And it's known that this Gaussian kernel emphasize or put more weights on smoother functions, meaning that for lower frequency functions, then you have this higher, bigger lambdas. So if you apply a Gaussian kernel, what it means is that this loss function will favor smoother functions, smoother value functions. And so how do we extend this to the control case where you have more actions? The different options. One is to introduce the pi variable here, and then do the same kernel loss trick as before, except that now instead of having a kernel function on pair of states, now you have a kernel function on pairs of state actions. And the same thing applies. It's more complicated, but it's the same thing. Another option is to use the previous loss function, assuming the policy is fixed, but then use it as a black box, as a component inside another meta algorithm like approximate policy iteration or actor critique to solve the policy evaluation problem. For example, in actor critique, this critique is essentially solving V when actor, the policy, is fixed. So you can use this loss function to learn the critique, and then use the critique to update actor, and then use this loss function to update the critique again. You can do this in this way. So now the question, now let's go back to the starting point why we have to go through this, is that there are benefits of looking at formulating the problem as optimization. And if you do this kind of dynamic programming based approaches, it's known that there are very simple examples that they lead to unstable or divergent behavior. An example is from Boyan and Mu in 20-something years ago. It's called Puddle world. It's essentially a continuous two-dimensional grid world with puddles. The agent wants to go from a start state to the goal state while avoiding the puddles. If you apply neural network and solve the problem, then they show in the paper, and it can be reproduced here, that the neural network can diverge to infinity. And this is the case here. So we have different approaches here. K-loss is our approach. What's important is the green line TD and fitted value iteration. These two are the DP-based approaches, green and blue. You can see the green and blue, they diverge to infinity, the magnitude of the weights. The value, the mean square error, or the value function, they go to infinity because the value function estimate goes to infinity. And then another thing to mention is residual gradient, which ignores the double sample problem. So the gradient in residual gradient is biased. And we know that we expect it to learn the wrong policy, and indeed it is. You can see that the mean square error doesn't decay that much. And if you look at the Bellman error, it can actually increase. And state that we covered previously, it's making progress, but then it's learning relatively slowly because solving the Primal-dual is not easy, so it may require extra work to make it work better. And in contrast, the K-loss function, we can have fast decreasing mean square error measured this way, and Bellman error. So for these two, the lower the better we want. And these two plots show that our loss is more consistent, more better correlated with mean square error of value function and Bellman error. So it's quite, the shape, the slope is not one, but then the correlation is high, meaning that the kernel loss, the K loss, is a good surrogate loss for reinforcement learning problems. And the similar result can be observed from carpo and mounting car, both classic examples where neural networks can diverge. And then we also look at more challenging problems in Majorco control problems, in particular these four problems. And we look at our approach K-loss and these two dynamic programming based methods, and this bias gradient residual bias gradient method, RG. And everything is used inside Trust PCL, which use value function learning as a component. So everything is the same except that we vary the algorithms for learning the value function so that all the comparisons are fair. Again, we see that the red curve, kernel loss, is the best performant. So to conclude, so a few take-home messages that it seems that now modern RL requires people to go beyond tabular linear cases. That has dominated the research in the RL community for quite a long time. And then when we talk about nonlinear cases, it seems that convergence conditions for DP-based methods become very brittle. It's very easy to break it so that it oscillates and diverges. And this can be observed in practice, and it's a bottleneck for applying RL in practice. And then I would like, hopefully I've argued in this talk that it's a promising and fruitful approach to shift from dynamic programming-based approaches to optimization-driven approaches, where you want to formulate a problem as a minimization or minimax function with objective function, and then solve it using more standard optimization techniques. And it has many benefits, such as improved convergence and stronger theoretical guarantees. Also, it has more transparent behavior, as you can analyze what the algorithm is doing using established techniques from statistics and machine learning. And finally, this is not just about theory. The long-term goal is to show that, okay, this theory and this new thinking can lead to algorithms that are easier to solve, easier to use in practice, so that you don't have to worry about different kind of strange behavior of the algorithm. Everything becomes more comparable to supervised learning, and you can, the tools can be off the shelf. So one day. And then there's this problem is drawing growing interest in the community, and with a few colleagues like Dale and Bodai and other people, we are organizing a workshop at Europe's this year. The topic is the optimization foundations of reinforcement learning, including this fixed point optimization and also linear programming and other optimization approaches to reinforcement learning. And you're welcome to participate and contribute. Thanks.
We have time for questions. So I'll ask one. So I guess back to my earlier question, I was saying that you motivated your approach by saying that you get these instabilities when you project the function class after the Bellman operator. So then in the last part, you were using kernels, but it wasn't clear how to fit DQN into this. So do you have a hope or a plan for how to try to smooth out DQN like you originally said?
Yeah, in a sense, this is doing what you were thinking. Here, we're learning VPy. Yeah, I should mention that although there's a kernel component in the loss function, this is different from the more traditional kernel-based machine learning. Here, our value functions are parameterized as neural network, and the kernel function is only used to construct the objective function. And so the difference between this and DQN, essentially, is that DQN, the objective function is different. Well, the optimization approach is different. In DQN, it's based on dynamic programming. So you use a target network to construct a target for regression and then learn the learning network and repeat the process. This is exactly dynamic programming. And we've seen that it can be unstable. And here, instead of doing that, we frame the whole problem as a single optimization problem and solve it. So it's more stable and hopefully easier.
What does K-loss means? The K-loss algorithm?
Oh, K-loss is, K-loss refers to the loss function using the kernel that here, this kernel, this loss function, also K. Here, this loss function is about finding the value function for a fixed policy. Okay? And this is what is needed by this trust PCL algorithm. I don't have to explain the whole algorithm, but essentially, it it has two components. One is to update the policy. The other is to learn the value function for that policy. And all these algorithms, competing algorithms, differ in how we learn the value function given the same policy.
So I think your algorithm is SDED, right? And not just that.
Yeah, so that's so this is the kernel one. You can think of that as a simplified version of speed. Speed is based on the Primal-dual formulation, and this kernel loss function is an approximate to the Primal-dual, approximating the dual part.
So I'm curious in cases, like if you take smaller problems where you could actually solve the dynamic programming reasonably well, do you have a sense of how much you might in fact lose by doing the, restricting the function to the RKHS instead of actually doing the full-blown max in the saddle point?
Yeah, it depends on. Good question, but it depends on how you restrict the RKHS. But you know some special cases. For example, you have a problem that you know that, well, if you have using a standard linear approximation, and then we use linear kernel, and then these two find the same solution. And then if you use the indicator function in the kernel to mimic the dot product, then you find the model-based RL. So everyone collapse to the same thing eventually in this simple special cases. But in general nonlinear cases, then they start to diverge. Well, they start to be different, not diverge. So.
Okay, let's thank the speaker again.